Okay, class, today we are going to do section 8.6 on probability, which is an application that can be seen in business a lot, sports, psychology, medicine. It's all across the board. You can see probability. So we are going to be working on games for one big application. Okay, so first off, some vocabulary. So we have the probability experiment. So an experiment is just, what are you going to be doing? So for example, you can roll a die. Okay, and it's an action which counts, measurements, and responses are obtained. So your experiment can be rolling a die, playing poker, giving medicine to small children to see what happens. You know, that would be an experiment. Okay, the next vocabulary would be a sample space. So sample space is the set of all possible outcomes. So example, if you roll a die, the set of possible outcomes are 1, 2, 3, 4, 5, and 6. Event. So the event taking place is you're rolling the die and you want to see, for example, the probability of being even. So it would be a subset of your sample space. So one event could be looking at the die being even, another one looking at the die being odd. Another event might be the die when after you roll it being less than 3. So those are different events that can take place that you might be observing. And the outcome is what happens when you roll the die. So if I roll a die, for example, maybe 4, that would be my outcome. Okay, so the experiment is what you're doing, so rolling a die. This sample space is what could happen. Those are all possible things. An event would be a subset that you'd be looking at, like find the probability of, or how many ways can the die be even. So the different things you might be interested in. The outcome is what actually happens when you perform that experiment one time. Okay, so here's an experiment. The probability experiment with action. Through which the counts, measurements, or responses are obtained. So for example, choose a car from a production line. That's the experiment. So there's going to be all these cars. Okay, so our sample space would be the set of all cars. And we have all of these cars all the way out. Okay, and the event is the subset of the sample space. So we have a few of them. That would be the event, a subset. And the outcome is which of those are taken? Well, one car was picked. Okay, so choose a car from production line. Here's the list of cars. I'm going to pick the green cars, or the sample, from the sample space. And the outcome is, well, I chose this car. Okay, so that is the outcome, the one you picked. Okay, so there's two different types of probabilities that we're going to be looking at. One would be the classic or theoretical probability, where everything, all outcomes are equally probable. And the notation P of E, so the probability of the event, like the probability you roll an even number, or the probability you get a heart when you get one card out of a deck. So the number of ways, essentially, it's the number of ways to get E divided by the number in the sample space. And we'll go through lots of examples. So some notation is the probability of E is the number in the event, so the number of ways to get event E, and the number in the sample space. And all probabilities is a number between 0 and 1. 0 meaning it's not going to happen, it's an impossible event, and 1 meaning it is certain to happen. It is likely. It will happen. You're 100% certain. The other type, so there's classic and theoretical, is empirical or experimental, and that's just based on frequency of things happening. So the probability of some event would be the frequency of event E divided by the total frequency. So for example, an experimental or empirical probability might have to do with floods, like you've heard the terms 100-year flood. That has to do with the frequency is it happens once out of every 100 years. And that, so it's called a 100-year flood. Another example would be looking at probability of blood pressure, so decreasing after you have some sort of medication. Okay, so that's based on some sort of experiment that was done with the drug. Okay, so here is the sample space and probability. So 2 dice are rolled. We have the blue die and the red die. Okay, so this is the list of all possible outcomes. That's the sample space. Okay, the blue die can be a 1 and the red die can be a 1, or the blue die can be 1 and the red die can be 2, all the way down. That's the all possibilities. That's the sample space. So find the probability that the sum is 4. So what we can do is we can look at, well, there's the 3 ways that the sum is 4. So there's 3 out of 36 possible ways. So the probability that you get a 4 is 3 out of 36, or 1 over 12. So we are going to reduce our fractions because there's 3 ways to get what we want, the sum being 4, and there's 36 possible outcomes in the sample space. So the probability is 1/12. Find the probability that the sum is 11. So we're going to go through, and there are 2 ways that the sum can be 11. So the probability that the sum is 11 is 2 over 36, or 1 over 18. And lastly, we are going to find the probability that the sum is 4 or 11. So the probability that the sum is 4 or 11, we look at the number in the sample space. So 4 or 11. So if the sum is 4 or 11, oops, went too far. Excuse me. So the probability that the sum is 4, well, the probability that the sum is 4, there were those 3 ways, and the sum is 11. There are 2 ways, so it's 3 over 36 plus 2 over 36, or 5 over 36, or translate to add. Okay, so now we are ready to move on to the next slide. And on the next slide, we are looking at complementary events. So the complement of an event E, or E with this little apostrophe, is E complement. An E complement consists of all events in the sample space that's not in the event E. So here is everything that could happen, and you can have E is green, and E complement would be everything not. So for example, if I roll a die, so here's rolling a die, and either it could be the event E being odd or E complement even. So if I roll a die, I know that it's either going to be odd or even. So if I sum up the probability of E plus the probability of E complement, it equals 1, because I'm 100% certain the die is either going to be even or odd. It's going to be one of those, even or not even. Or if I solve, the probability of E complement is 1 minus the probability of E, if I just bring E to the other side. So for example, the day's production consists of 12 cars, 5 of which are defective. 1 car is selected at random. Find the probability it is not defective. Okay, so what we can do is we can find the probability of being defective is 5 out of 12, because 5 are defective. So to find the probability it's not defective, so that's the complement, so the probability of it not being defective is 1 minus 5 over 12, or 7 over 12. And a lot of you can just do that directly in your head. Well, if 5 are defective, 7 are non-defective, so the probability of it not being defective is 7 over 12. Okay. So moving on, independent events. 2 events, A and B, are independent if the probability of B is not affected by the occurrence of A. Okay, so what that means, so for example, when it doesn't depend on A being female and B having type O blood, it does not matter. You having type O blood does not depend on you being female or not. Okay, one does not depend on the other. Okay, so the opposite is 2 events being dependent, being a female and being under 64 inches tall. Well, being under 64 inches tall, if you are under 64 inches tall, most likely you are a female. So it is dependent, okay, because they're not completely separate from each other. Okay, taking aspirin each day and having a heart attack. Well, studies have shown taking aspirin each day does reduce having a heart attack. Okay, if your first child is a boy and the second child is a boy, if your first child is a boy, that in no way affects the gender of your second child. So the gender of your second child is not affected at all, the probability, by what the gender of your first child is. They're completely independent events. Multiplication rule. 2 dice a roll, find the probability that both are 4s. Okay, so the probability that the first die is a 4 and the probability that the second die is 4. So the probability that the first die is a 4 is 1 out of 6. And the probability that the second die is a 4 is 1 out of 6. So the probability of A and B, A means multiply. Remember, and means or? Sorry. Probability of A and B, we are going to multiply. When it was or, A or B, like when the sum was 4 or 11, we added. So, or, add, and multiply. Okay, so this is the rule. If the two events are independent, okay, so B having nothing to do with A, right, what you get on the first die does not at all affect the second die. Okay, mutually exclusive events. Two events A and B are mutually exclusive. They cannot occur in the same trial. So, for example, a person is under 21 and a person is running for the U.S. Senate, because you have to be over 21 to run for the Senate. A person who was born in Philadelphia and a person who was born in Houston. You cannot be the same person if you were born in both cities. Mutually exclusive events. So in a Venn diagram, you would have a circle that represents A and a circle that represents B, and the probability of you being in both of those circles, A and B, would be 0. Okay, because you're either here or here. Mutually exclusive. They're separate. Okay, non-mutually exclusive events. So this is when you can have some sort of overlap. Okay, so a person is under 25 and a person is a lawyer. There's a group of people that are under 25 and a group of people that are also lawyers. Same thing. Born in Philadelphia and watching TV, that can be the same person. So it's non-mutually exclusive. So if you have a circle that represents the people born that are under 25 and another circle that represents the lawyers, there's this overlap of the under 25-year-olds who are also lawyers. So that's non-mutually exclusive. And that's when the probability of A and B does not equal 0. The probability of A and B is this overlapping section. Okay, the addition rule. So, the addition rule, so I alluded to it, the probability one or the other two events will occur. So you'd find the probability of A and the probability of B and subtract off their intersection. And if they are mutually exclusive, then the intersection would be 0. Okay, so a card is drawn from the deck. Find the probability is a king or it is red. Now, if you pull one card from a deck, can it be a king and red? Are they mutually exclusive? Well, no, they're not mutually exclusive because you can pull a red king. So we're going to find the probability that you get a king. That's the probability of A. There are 4 out of 52 cards in the deck that are kings. B, the card is red. 26 cards are red out of the 52. And the probability of A and B, well, how many red kings are there? Well, there's 2, the king of hearts and the king of diamonds. So the probability of A or B is the probability of A plus the probability of B minus the probability of the intersection. So in a Venn diagram, you have A, you have B. So we found the probability of the whole circle A, found the probability of the whole circle B, but we counted this part twice, so we're going to subtract it off once. So then you just reduce your fraction and you get 7 over 13 when you reduce your fraction. Okay. So, the addition rule. Okay, so here a card is drawn from the deck, and we want to know the probability of the card is a 10 or a king. Well, are there any cards that are kings and a 10 simultaneously? You pull one card. Now, those two are mutually exclusive, so the probability of A and the probability of B, and the probability of A and B. So there are 4 kings, 4 10s, and there are 0 that are both. So the probability of A and B is probability of A. So there are 4 kings out of 52, 4 out of 52. Subtract off the intersection, reduce your fraction, you get 2 over 13. Okay, so that is the end of video number 1, and we are going to move on to video number 2.